Hello and welcome to this talk. My name is Masood, and in this presentation I will talk about the accuracy of resilience parameters in sheep and goat. Resilience has different definitions, but the one we use here is the ability of the animal to remain productive under challenged conditions, which is normally estimated by fitting a line through the performance data on different challenge levels. The inverse of the slope of this line is the resilience indicator, and the intercept shows the performance potential in an optimal environment. Ultimately, we want highly resilient individuals that have high performance potential as well. But the two roadblocks are that first, often there are only a few data available for an individual, and hence the fitted line is not accurate. Of course, pedigree information can be used to rectify this to some extent, but we are also interested to learn how genomic data can improve the accuracy. In addition, we seldom know the exact environmental challenge level an individual faces, and this is the harder bit. So here we will be looking at the factors that affect the accuracy of the parameters, slope and intercept, or resilience and performance potential. In specific, the research questions we seek to answer is the impact of the distribution of the phenotyped animals on the accuracy. Also, it is believed that there is most likely a trade-off between parameters between slope and intercept, that is a genetic correlation. So we are also interested to assess the effect of genetic architecture on the accuracy. And finally, we want to know how does not knowing the environmental challenge level affects the accuracy. For this simulation study, we simulated the genome of a population of sheep. From that, we simulated a 3-generation half-sheep pedigree with all animals being genotyped and only the middle generation being phenotyped. The phenotypes for the second generation were simulated with a linear model, similar to the first slide that I showed, intercept plus challenge level times slope. The parameters intercept and slope are assumed to be deviating from their mean by a genetic and an environmental factor. Both parameters were simulated once with high heritability of 0.3 and low of 0.1, and 3 genetic correlations minus 0.5, 0, and 0.5 were assumed, where the negative genetic correlation indicates a trade-off. A bottom-up approach was taken by first assuming the environmental challenge levels are known, and then the variance components and the parameters were estimated. In the second step, the challenge levels were also assumed to be unknown and hence had to be estimated prior to REMOL or blob analysis. The accuracy, by which I mean the correlation between the true breeding value and the estimated breeding value, as well as the degree of bias, which is the regression coefficient between the true breeding value and estimated breeding values, were estimated. To understand the impact of the phenotyped animals on the accuracy for the estimated breeding values of intercept and slope, 3 scenarios were considered. In the first scenario, that represents, for example, artificial insemination, we assume that all the individuals are randomly distributed across all the environmental range, so any sire can have its offspring in any environmental condition, or different farms, if you like. In the second scenario, the individuals are clustered into families. Basically, the offspring of a sire live together in a small range of environment. In the third scenario, which is a special case of the second scenario, the offspring of a sire live together, but a good sire is reared in a good farm and a bad sire is reared in a bad farm. Hence, we use the term assortative, and it should not be confused with the assortative mating. We call this a scenario assortative because of the reason I just said. A good sire lives in a good farm, and so on. So for all these scenarios, we estimated the genetic component and the breeding values of the parameters intercept and slope, once using blob and another time using gblob, and these two were compared, blob and gblob. That is, the comparison was done basically through comparing the accuracy and the degree of bias in the estimated breeding values for the third generation. So here's the result for accuracy. In this figure, we have the accuracy of intercept, the two figures on the left, and slope, the two figures on the right, that are calculated using gblob, the two on the top, and blob, the two on the bottom. On the x-axis, we have different scenarios. So each pair of bars represent one scenario with colors representing high or low heritability. The first thing that we can see, as expected, is that the genomic information massively improves the accuracy, sometimes up to a factor of 2 or more. We can also see that when using equal heritabilities for performance potential and resilience, the accuracy for performance potential for the intercept is generally higher than that of for slope. Across different scenarios, also, we see that random allocation of individuals gives the best estimate, although the slope does not show much of variation of prediction accuracy across different scenarios, whereas intercept is generally more sensitive. The bias in the result also improved when heritabilities were higher or when we used gblob. So the regression coefficients became closer to 1. However, there was no significant difference between the regression coefficient of the two parameters or between different scenarios. So the second question we wanted to answer was the effect of genetic correlation on the accuracy and bias of estimated breeding values. So here on the left figure, you can see the accuracy of the parameters with different colors that are estimated with gblob, solid line, and blob, the dashed line, for different scenarios. And you can see that the relationship is direct and almost linear, in fact. As the genetic correlation increases, the accuracy of the estimated breeding values increase. For the regression coefficient, there was no direct or indirect relationship, but we saw that the uncorrelated data were in fact more biased as they had high regression coefficient comparing to correlated data, and they were underestimated basically. So the last question we wanted to answer was to assess the effect of not knowing the challenge levels. To estimate breeding values when the challenge levels are not known, we use the famous two-stage reaction norm model that involves fitting an effect for the farm and then using that farm effect as the challenge level for all the animals that live in that farm. That means basically if we have a very heterogeneous farm in terms of challenge level that covers a wide range of environment, farm A, as you can see from this little sketch, comparing to a less heterogeneous farm that covers only a small range of the whole environment, farm B. And because each farm is represented with a single value, our estimate for farm A should be poorer than farm B. So the hypothesis was not only the unknown environmental challenge levels reduces the accuracy, but also the extent of the farm has an impact on the accuracy. So for that reason, we considered 3 scenarios: farms covering 30% of the whole environmental range, and this is indicated by RN30 on the x-axis of this figure. Farms covering 20%, RN20, and RN10, which is farms covering 10%. RR on the x-axis is the previous case, which is when we know the environmental challenge, and finally RR star means when both challenge level and the genetic parameters are known, which is the best case scenario, and it's just there as a reference point. So this figure shows the accuracy of resilience and performance potential under these scenarios or a type of analysis. And the different colors show different genetic correlation between intercept and slope. So blue is 0.5, green is 0, and red is minus 0.5. Here, gblob is used, and the individuals are allocated at random. So what this graph is basically telling us is that if we have positive genetic correlation, we do not need to worry about not knowing the challenge level, as the blue dots have the same value more or less. But most likely in many cases, there is a trade-off between performance potential and resilience.
And so we have to look at the red dots.
So looking at the red dots, basically genetic correlation and different ways to allocate phenotype individuals, we obtain this figure. So here on the x-axis, again, as before, we have these 5 different analysis types that I explained. Here, different colors show different way to allocate individuals. So the cyan color is the random allocation that you have already seen in the previous slide. The green is the assortative cluster, and the red is clustered groups. So again, we see that random allocation sits always on top of the other two. Although for slope that is not very significant, it's not by far, but still we see that random allocation in all the environments, in all the analysis gives the best accuracy.
So in conclusion, we see that genomic data increases prediction accuracies for individuals' resilience and performance potential, sometimes more than 2 times. Prediction accuracies depend on how genetically related animals are distributed across herds. We always obtain best accuracy when individuals are allocated at random for both intercept and slope, although the slope is less sensitive to the way individuals are distributed. And in general, the performance potential or the intercept was better estimated than slope. In addition, an existing trade-off between resilience and performance reduces the accuracy. In fact, life is easy if there is no trade-off, as we don't need to know the challenge levels for animals. Finally, using GBLOB or random allocation can help us obtain good accuracy even in the presence of trade-off and unknown environmental challenge levels.